session today. Yeah, what did you think? So, yeah, so question and answer today. I got their attention, but I know what gets their attention. It's not chemistry. Okay, so last time, what did we talk about? We talked about the fact that reactions, that alpha halocarbonyl compounds, talked about how to make them, but we also talked about their reactivity. And it's useful to think of these as being kind of a special case of an allylic halide, okay? So we know that allylic halides have special reactivity, and so if you think about it, it's sort of like an allylic halide, and they're reactive. They're reactive towards SN2 reactions. Okay, we're going to make a distinction here. There is a little bit of a trick though, because you have to be careful that the nucleophile that you use is non-basic. And the reason it has to be non-basic, I think you can see that once you have the halide there, you've acidified this proton. So if you have a basic nucleophile, then there's going to be a competition between an acid-base reaction, which will convert this into an enolate, and the SN2. Now, recognize that once you get the enolate, then the enolate is going to be completely unreactive towards substitution, right? Because you'll have a negative charge on that carbon atom, you're not going to do an SN2 reaction there. So that's why you need to have non-basic nucleophiles like methyl sulfide. These reactions work really well. It's a reactive electrophile, not particularly reactive nucleophile, but the reaction goes nicely because you don't get proton transfer. If you get proton transfer, you're screwed. Because at that point, no reaction is going to take place at that carbon atom because it will have a negative charge. Now, this is the situation that obtains for alpha bromo ketones and alpha bromo aldehydes. But when you go to, or alpha halo ketones, alpha halo aldehydes, when you go to alpha halo acids, not a problem. You can use basic nucleophiles to your heart's desire. And the reason is because something else happens first. You end up pulling off that proton first to get this carboxylate. This dianion never will form. You need a heck of a strong base to make the dianion. And so this is still an allylic halide, and this will still undergo nucleophilic substitution reactions. And so this reaction of a alpha halo acid with a nucleophile is actually done on huge scale, because this is the reaction that gives 2,4-D, which is a herbicide that's commonly used. So it's not Roundup, it's the earlier generation, harder, less environmentally friendly herbicide. So phenoxide, which you get with sodium hydroxide, so sodium hydroxide forms the alkoxide and phenoxide. And then phenoxide just does a displacement on the chloride. So phenoxide displaces that chloride. And the reason that you can use strongly basic conditions here is because once you form the carboxylate, there's no way you'll ever get the dianion. Dianion just will not form. So this reaction works really well. Now, these are all, the two examples I gave you are SN2 reactions. Okay, SN2, nucleophilic substitution bimolecular. Now, what you're not going to get with an alpha halocarbonyl of any kind is you're not going to get an SN1. Remember what the difference between an SN1 and an SN2 is, right? So for an SN1 reaction, you end up, for an SN1, you have, say, a halide here, say a chloride. You end up with a unimolecular process to give you the cation and chloride. And then this is what reacts with the nucleophile. Up to here, good. But if I put an electron withdrawing group on any one of those carbon atoms, then what have I done to this cation? Already has a positive charge. If I have an electron withdrawing group here, I'm pulling electron density out of a cation. That's no good. And so that cation is not going to form. And so that's why you're not going to see SN1 reactions with alpha halocarbonyls. Because if I were to ionize that, I'd end up with a cation here, which is right next to a positively charged carbon. Carbonyl carbon atom, remember, has a partial positive charge. Two positive charges together, no good. That's what I said moments ago. Now, you might be tempted to say, yeah, but this is resonance stabilized. Well, okay, so let's draw the resonance structure. The resonance structure for this, right, the resonance structure places a positive charge on oxygen. Now, what did we say about positive charges on oxygen and electronegative atoms? Only when the oxygen atom has a complete octet. But this is an electron deficient oxygen atom that's missing its octet, and it has a positive charge, therefore no good. And so essentially you don't have this resonance contributor. This doesn't contribute anything to the structure. And so these cation, this kind of cation, you can actually form these cations, but when you do form them, they're just extremely reactive. And so you surely won't form them by Solvalis' reaction. So bottom line, alpha halocarbonyls are good for SN2 reactions only. They're reactive, but reactive only for SN2. Okay, so now let's get back to a reaction that I kind of very briefly mentioned, I think on Monday. And that's the aldol addition and condensation. So this is a very important process. And so how does it work? Well, it works by taking an aldehyde. Ketones also work, but let's start with aldehydes. Take an aldehyde and treat it with base. And two of the aldehydes come together to give you a dimeric structure where we have an aldehyde and a hydroxy group, so therefore aldol. This is a carbon-carbon bond forming reaction, so already you know this is important. Now, why does this work? Well, you have to remember what I said about carbonyl compounds. And I said that when you have a carbonyl compound, let's just take a generic species like this that has alpha protons. Remember that I have two kinds of reactivity associated with this species. This is a partially positively charged carbon atom, which means that nucleophiles will attack here, but these protons are acidic, and so they can be removed to form from here either an enol or an enolate. Let's just show the enolate. So the enolate looks like this. And so this carbon atom is electrophilic. And this carbon atom is nucleophilic. And so I have this dual reactivity. Well, you see that dual reactivity in the aldol, because one of the aldehydes, the one on the right as I've shown it, is the nucleophile, so the enolate was where I'm pointing. The other carbonyl group acted as an electrophile, and so the negatively charged carbon atom reacted with the positively charged one, and you got the CC bond. Okay, so now let's take a look at the mechanism that shows this explicitly. So this is base catalyzed. Hydroxide, and this is reversible, of course. Hydroxide reversibly pulls off that proton to form an enolate. That enolate is nucleophilic, as I've shown. That carbon atom has a partial positive charge, shown here, and so I can push arrows like so to form a red bond between the CH2 here and what used to be the carbonyl. And so once I form that bond, I will have this red bond right there. So that came from that CH2. There's the CH2, the carbonyl, there's the carbonyl. Proton transfer completes the process, and I end up with an aldol addition. Okay? Now, this reaction is reversible. And so it's more favorable for aldehydes than ketones, as you would expect, just given the greater reactivity of aldehydes versus ketones. And it forms, in both cases, a carbon-carbon bond. Now, this was a special case of an aldol reaction, right? Because the two aldehydes were the same. Acetaldehyde is the nucleophile, acetaldehyde enolate is the nucleophile, acetaldehyde is the electrophile. Acetaldehyde, acetaldehyde. You can already see that nobody said I had to pick the two aldehydes to be the same. I could have picked two different aldehydes. Once you do that, as we're going to see, there's a lot of complexity that results, and controlling that turns out to be an issue. Okay, now, if this reaction stops here at 0 degrees or at low temperature. If you let this reaction go longer or hotter then you end up eliminating water from here, and you end up with an alpha-beta unsaturated aldehyde. So this is the alkyl addition product. This is the alkyl condensation product. I apologize for the terminology. It would be nice if you could remember that, but it's not essential at this point. So addition reaction just gives you the alkyl. Condensation gives you the alpha-beta unsaturated. Condensation reactions, remember, are always of this type. A plus B react to give C with splitting out of a small molecule, typically water, but not necessarily water. So any reaction where, you know, A plus B, two of these come together, and then split out water is a condensation. Now, the mechanism for the second step, this step here, is a bit weird the first time you look at it, because it seems to fly in the face of something that I hammered into you. And so look at what happens. In the second step, hydroxide, there it is, pulls off the alpha proton to form the enolate again. So you can still form an enolate. And then I can push arrows to expel hydroxide right there to generate the alkyl condensation product. Now what's wrong with this? I mean, I start out with hydroxide, I end up with hydroxide, so great. So hydroxide is a catalyst, it gets cycled. What's wrong with that process? Something's definitely wrong with that. I mean, it works, but you know, it throws up a red flag for you. What's the red flag? Yeah, hydroxide is a really lousy leaving group. It's a strong base. So hydroxide is a very poor base. I mean, a very poor leaving group, strong base. So how does this work? Why does this work? And that's a very legitimate concern. After all, you know, or at least I hope you know, that if you have no carbonyl group here, that's just the same molecule without the carbonyl. You treat that with hydroxide, hey, nothing's going to happen. There's no reaction possible here, nothing. Okay, but you put a carbonyl group, well, not here. I guess that should have been on the other carbon. But if you put a carbonyl group here, then yeah, you're going to get the alkyl product. So these two reactions are distinguishable. The reason it works, actually, two reasons. First of all, you're never going to be able to pull that proton off without some help, right? This is just it's not in any way stabilized by the anion. It's not stabilized by resonance or by anything else. On the other hand, when you pull off the proton from here, the anion you form is resonance stabilized, and it's actually an alkoxide, right? So not only is it resonance stabilized, I can put the negative charge on an electronegative oxygen atom. Not so here. If I pull that proton off, there's no way to delocalize it, and certainly there's no way to end up with a negatively charged oxygen atom, because there is no oxygen there. So that means that hydroxide is not going to be able to pull that off, that proton easily, whereas this kind of enolate, this kind of anion, resonance stabilized enolate, where the negative charge can end up on an electronegative oxygen atom, that kind of anion, easy to make, okay? One reason. The other reason is because the condensation product is an alpha-beta unsaturated carbonyl. Remember what we said about alpha-beta unsaturated carbonyls. They are resonance stabilized. I can write 3 resonance forms for alpha-beta unsaturated carbonyls. And so, the product of the loss of OH minus, the alpha-beta unsaturated carbonyl, is resonance stabilized, stable. That means, from Hammond's postulate, that the transition state that leads to that stable alpha-beta unsaturated carbonyl is also stable. And so for these two reasons, a reaction that looks as if really it shouldn't work, works quite well. And so alkyl condensation reactions are very easy to do, as we will see. Now, the question, of course, is how do you know where it stops, right? And there's no, there's really no hard and fast rule for that. Very often, if you're trying to do an alkyl addition, you end up getting some of the elimination of condensation product. But the basic thing is that if you do the reaction under the minimum conditions of temperature, usually it stops at the alkyl addition with base. With acid, you always get the condensation. So acid-catalyzed alkyl reactions, also known, here it's with a ketone, acetone, and this always gives you the alpha-beta unsaturated compound. So how does this work? Well, it always works the same way. It works by forming the enol, and then having the enol, which is nucleophilic on carbon, attack the electrophilic carbonyl. Now, implicit in all of this discussion is something that, I haven't spelled it out, but let's do it right now. Let's just say that I start out with acetone, right? And I very quickly somehow convert it entirely into acetone enol or enolate. Am I going to get an alkyl process? It's all enol or all enolate. All of it. I have the nucleophile, that's the enol or the enolate, but I don't have the electrophile. So the answer is no. In order to get an alkyl reaction, you need two things. You need the enol or the enolate and the ketone. They have to be both present. Otherwise, you'll have only the nucleophile and nothing for it to react with. Okay, so it's important to recognize that you end up with a small amount of the enol and namely and primarily the ketone. But this is reactive, and the ketone here in acid is going to be activated. Notice the difference between the acid catalysis and the base catalysis, always the same. Whenever we have acid catalysis, then the electrophile is going to be the activated carbonyl, activated by acid-base reaction with in this case, with the proton. Why is this a more reactive electrophile than that? This is a more reactive electrophile because this is a cation. Easy, easy, So I form the red bond here again. Which red bond? This red bond. And that gives me the alkyl addition product from as the initial product. So this is the alkyl addition after loss of a proton. I've summarized some steps here. You lose a proton from here to give the enol, and then you add a proton here. So you lose a proton there, you add a proton there, 2 steps, and then this is a good leaving group, and you expel that in the same way that we saw before for hydroxide, and you end up with the alkyl condensation product. Now, the things to watch for are always the same ones, the same common mistakes. If it's an acid-catalyzed reaction, you're not going to expel hydroxide, right? Because the reaction to expel water, activating the leaving group, is going to be so much faster than loss of hydroxide. And so you don't generate hydroxide out of this reaction. Your leaving group here is water, good leaving group. So, in the case of the acid-catalyzed alcohol, the acid does 2 things for us. It catalyzes formation of the enol. Okay, so you need acid to form the enol, and it activates both the initial nucleophilic addition, and it activates, so there's 3 things. Catalyzes the enol, activates the carbonyl towards nucleophilic addition, and forms a better leaving group than you have with hydroxide. With the base catalyzed reaction, the only thing the hydroxide does is it does 2 things for you. There, it enables the formation, or catalyzes the formation of the enolate, not the enolate, the base, and it catalyzes the expulsion of not water, but hydroxide as your leaving group. So the 2 reactions are essentially the same, given all the differences that you've by now learned between acid and base catalyzed addition mechanisms. Well, okay, so nucleophilic species in the acid solution is the enol and not the enolate. Why? That's a trick question. The reason, of course, is because if you have the enolate, it's strongly basic. Where the heck are you going to find strong base in an acid solution? So, of course, the nucleophilic species in the acid catalyzed reaction has to be the enol, not the enolate. Okay. Now, I mentioned that I picked a kind of a loaded example of acetaldehyde plus acetaldehyde, acetone plus acetone. These are symmetrical alkyl additions or condensation reactions. But nobody said I had to do it symmetrically, right? I could have had an unsymmetrical process where I have 2 different aldehydes coming together in an alkyl addition. Let's just leave it at the addition. Is this going to be useful or not? And the answer is, well, probably not, right? Because I can form the enolate here and have this attack that aldehyde. I can have the enolate form here, that attacks that aldehyde. I can form the enolate here and have it attack the same species. I can have the enolate here and have it attack the same species. So I end up with all 4 possible combinations. And so in the most general sense, this is not going to be useful. And then on top of that, if I do the alkyl condensation, I have maybe a possibility of E and Z isomers. And so it gets complicated quickly. And so the first time you look at this, you say, well, you know, this is only going to be good for symmetrical cases. Not so. Because there are some special cases for which even this reaction can be useful. And we're going to see those right now. So the question now is, can we make a crossed alkyl? The non-symmetrical one is known as a crossed alkyl. Can we make a crossed alkyl useful? And we used to do this actually in Chem 273 lab. Benzaldehyde and excess acetone, a little bit of hydroxide, and end up with benzyl acetone, this stuff. And look, yield is really, really good. This is one of these idiot-proof reactions. You know, if you mix these two things together, there's just no way to screw it up. And so this tells you that this is an easy process. Now, why does this work? This is a crossed alkyl, but as I point out, this is a very special case of a crossed alkyl because why? Because benzaldehyde can't enolize it. This can only act as the electrophile, can't act as the nucleophile. Now you can say that, well, but you know, acetone can act as both the nucleophile and the electrophile. So why don't I get acetone condensing with acetone, and so I would end up with 2 products. And so why is it that, given that I'm using an excess of acetone, why don't I get this as a significant reaction product? And the reason is because the aldehyde, remember, is much more reactive as an electrophile than the ketone. And so the only enol or enolate you're going to form is from here. And then that enolate has a choice. It can react either with a really reactive carbonyl or with unenolized acetone. And so the desired reaction, given that this is the desired product, the desired reaction is faster, a lot faster. Also, if you ever did get the alkyl addition product for the acetone, that is reversible. And so that's never going to be an issue. And now the question is, well, okay, so why did we have to use why did we use an excess of acetone in the first place? I mean, you need to do, if this is your target, you need to use an excess of acetone. Why? Think. So the way you answer that question is you think about, well, okay, so what would have happened if I hadn't used an excess of acetone? What would have been the difference in product? So if I use, say, a 1-to-1 mixture, benzaldehyde acetone, or a 2-to-1, 2 benzaldehyde, 1 acetone, what's going to happen? Now think of the mechanism. You'll get here, right? Can this thing enolize? Can this enolize? Yeah, sure it can. If you form the enolate here and it sees benzaldehyde, what's going to happen? Okay, so if this thing enolizes, look what happens. And then if that sees benzaldehyde, that's going to form that, okay, as your initial product. And then with base, proton transfer, proton loss, elimination. So let's just cut to the chase here. You're going to end up with a nice yellow compound, this stuff here, which is dibenzyl acid, not benzyl acetone, but dibenzyl acetone. And so if you don't use an excess of the acetone, that's what you get. And that was the other experiment that the undergraduate lab used to do. So you can suppress that dibenzyl acetone just by using an excess of acetone. It's simple. Okay, so take-home lesson here is that in general, the crossed-Elbow reaction, the crossed one is the one between two different carbonyl compounds. The crossed-Elbow reaction will only be a useful process when there's some reason to expect a single product to form, okay? And so when the formation of one product is strongly favored, then that would be useful. So let's take a look at some other crossed-Elbow reactions. In this case, an intramolecular one. So if I have this dicarbonyl compound, this is a 1,5-dicarbonyl. If I have that 1,5-dicarbonyl compound and it undergoes a intramolecular alkyl condensation reaction, I end up with this single product, okay? So this is the alpha-beta unsaturated carbonyl. Where this ketone was is right here. So this carbon atom is the methyl. So 1, 2, these are these two methylenes, carbonyl, that's that carbonyl. This carbon atom is that methyl. And where the ketone was, I have a double bond, and of course I've lost the elements of water to get there. Okay, now, why is it? Okay, so in other words, in order to get this, I had to form the enol at the methyl site. That enol had to react with that carbonyl. But I could form an enol here. I could form an enol there because there's an alpha proton there, or I could form an enol here as well. Why is it that I only see one product, given the fact that I could have formed 4 enols, and each one of those would have presumably led to a different product? Why is that? So how do you answer a question like that? I mean, it's, you know, the fact of the matter is you only see one product, but the question that you need to answer is why? Well, you look at what the other products would have to be, and then once you look at the structures of the other products, it should jump off the page at you why you don't form these. So let's just take one example here, okay? So I'm going to draw that compound a little different. I'm going to draw it like so. So let's just say that I formed the enol at this position, okay? Now, if I enolize it there, what will I end up with? I'm going to end up with this enol, right? Now, if this enol reacts like so, and this is an acid, so it's going to be activated. If it reacts like that, what's the size of the ring that I'm going to form? Count. Four, right? 1, 2, 3, 4. So now you know why you don't form that one, because the 4-membered ring is strained. And you can go through the other ones and figure it out for yourselves why. So these reactions are reversible, and so you have a chance of forming the thermodynamically favored alpha-beta unsaturated ketone. Now let's take a look at synthesis with using the alkyl condensation. Now it turns out this is a very important tool for organic synthesis, but you have to apply it with knowledge of the mechanism, or you're going to screw up. Okay, so let's just say I have this as an alpha-beta unsaturated ketone. So somebody says, you know, I'm going to pay you a lot of money to make me a kilogram of this stuff. And so I see, oh, well, good, I have a ketone's alpha-beta unsaturated. So if I have benzaldehyde as the electrophile, then this would be the nucleophile that I need to form the enol or the enolate at that site, add, and so on. Now, the question is this going to be a useful process or not, given what I've just told you? Think. So what's going to determine if it's useful or not? It's going to be useful if you can get one product. If you get, 10 different products, no good. Well, we're almost there, maybe, because we have benzaldehyde as the electrophile. Benzaldehyde cannot enolize. So at least the one partner, the aldehyde, is going to act only as the electrophile, not as the electrophile and nucleophile. So that part's good. Now, how about the ketone? Does the ketone give me one enol or enolate or 2? Yeah, it gives you 2 because the 2 sides ain't the same. So this is not going to be any good at all. Why? Well, because I've shown this kind of suggestively as if it's going to enolize here. But guess what? The other methylene can also enolize, and the 2 enols are not the same because this is an unsymmetrical ketone. And so this is not going to be a useful alkyl reaction as shown. So the question is, are there other ways to make this? Of course there are, but not this way. Okay, so you need to kind of be aware of the limitations. Now, alkyl reactions take place between ketones and aldehydes, aldehydes and aldehydes, aldehydes and ketones, and so on. But of course we have other carbonyl compounds. Those other carbonyl compounds also form enols or enolates. Those enols or enolates are also nucleophilic. And so you can imagine that those can participate in reactions that are completely analogous to the alkyl, and you would be right. And so what are some of these? Well, one of them is the Claisen condensation. So if you take ethyl acetate and you treat it with sodium ethoxide, now this is not a catalyst, right? You have to use this stoichiometric there, superstoichiometric. And then you end up with a beta ketoester. You end up with ethyl acetoacetate. Alpha carbon, beta carbon. Beta carbon is a ketone. This is an ester. It's a beta ketoester. Okay, so you end up with ethyl acetoacetate. That's a very good beta ketoester synthesis. Now, how does this work? Well, you kind of know how it works, right? I have an enolizable ester. I have a base. So the first thing that's going to happen is I'm going to pull a proton from here reversibly. That's going to convert ethyl acetate into its enolate. The enolate is a nucleophile. The unenolized ester is an electrophile. And so it's exactly the same mechanism with a little twist, as you will see, as the very first one that we talked about this morning, the base catalyzed alkyl. So here it is. Now, take a look at the pKa's though, because that's going to become important. So you don't have to memorize these, but you know that this is not nearly as acidic, that proton's not nearly as acidic as a ketone or an aldehyde. And so the equilibrium is going to greatly favor this and not that, because pK of ethanol is around 15 or 16, this is 25, so you have a tiny little bit of this, but this is reactive, and so it sees unenolized ester, and it does the same kind of addition to form a tetrahedral intermediate. The tetrahedral intermediate here spits out ethoxide, which is a leaving group. We've seen that kind of leaving group with the alkyl condensation. That gives you the beta ketoester. Now, this proton is much more acidic than that one. Look at that. It's got about 10 to the 15th, 10 to the 14th, 10 to the 15th difference in acidity between product and starting material. And so ethoxide is going to quickly pull that proton off. And what you're going to end up with as your product is going to be the beta ketoester enolate. Now, that turns out to be critical because the thermodynamics do not favor the beta ketoester, do they? And you kind of know that because remember what we said about stabilities of carbonyls. Which is more stable? Well, let's take it the other way. Which is more reactive, a ketone or an ester? Which carbonyl group is more reactive, ketone or ester? I'm listening. Well, which is the most, of all the series, which is the most reactive? Acid chlorides, anhydrides, aldehydes, ketones, esters. So the ketone is more reactive than the ester. The ester is more stable. So look at what you've done here. You started out with 2 esters, 2 stable ones. You've converted it into an ester and a ketone, stable, less stable. So just from that very simple argument, the little warning sign should go off in your head saying, this doesn't look like it's going to work. Because I'm starting with something that's stable and I'm converting it into something that's less stable. So the reason this works is because this reaction is completely irreversible. And so you end up, this has got a pK of 10.7, ethanol is 10 to the 16th, so you've got about a millionfold difference in acidity between that proton and that one. And so it's the formation of this enolate under basic conditions that provides the thermodynamic driving force. If you can't form that enolate, guess what? No Claisen takes place for the reason that I indicated. So the only kinds of Claisen condensations that will take place are ones where you will be able to form an enolate, and then you can trap this in workup by working this up with acid. So once you acidify it, it's okay. But certainly in base, you have to be able to form that enolate, or this process favors starting material. So here it is. The overall equilibrium favors the starting materials, and it's only the irreversible formation of the enolate of the beta ketoester that enables this process to go to completion. And so that's why you need a full equivalent of sodium ethoxide. So if you try to do this reaction with anything less than a full equivalent of sodium ethoxide, it won't go. It also won't go if you have an ester like this. So if I try to do this kind of Claisen condensation, this reaction doesn't work. Why? Well, because look, once I do the condensation, I have a methyl and a methyl, not a hydrogen and something else. So there's no way to form the enolate of the product. Therefore, the equilibrium favors starting materials. Therefore, it doesn't go. And so, so that's something to keep in mind. Now, the other thing that you want to notice is that I chose the base very deliberately. I started out with ethyl acetate, and so I used sodium ethoxide. If I'd started out with methyl acetate, I would have chosen sodium methoxide. Why is that? Well, because you'll get transesterification reactions for sure. And the transesterification works this way, where an ethoxide comes in, gives a tetrahedral intermediate, and it spits out ethoxide. But because ethoxide and ethyl, nothing changes. But if it were methoxide and ethyl, then I'd end up with a mixture of methyl esters and ethyl esters, and that might not be too useful, right? Because I end up with a mixture of two products. So that's why you end up choosing the base to match the ester. Now, this is important. I want you guys, in this chapter particularly, we're going to go through a lot of mechanisms. And these mechanisms are each a little bit different from the last one that we discussed, but in one sense, they're all the same too. And so what you absolutely have to do for yourselves is to look for the common features of these mechanisms. Don't treat each mechanism like a separate entity or a separate set of facts to memorize, or you won't be able to solve problems. Okay? So look at these mechanisms and try to discern the logic behind them and the commonality. In all cases, and I've tried to do that in class, but you have to sit down with pencil and paper and do it yourselves, or it won't make sense to you. In all cases, they follow the same logic. And in all cases, it's usually addition to a carbonyl, tetrahedral intermediate. The tetrahedral intermediate does something depending on what it's attached, what the substituents are, proton transfers, and so on. It's always going to be the same, with little differences, right? And so please try to understand that rather than looking at each one of these things as a separate fact. So when you do problems, I think it'll become easier. Now, there's an intramolecular version of the Claisen condensation that's particularly useful for making rings. So remember, the Claisen condensation that we talked about moments ago was between ethyl acetate and ethyl acetate. And so it was a bimolecular process. But the one that I've shown here is a diester. So I have a compound that is linear and has esters on either end. And so when I form the enolate at this site, that enolate can attack that carbonyl to form the red bond. And this tetrahedral intermediate, which then eliminates ethoxide. What drives the process is that I have a proton there, so I stabilize the product by formation of an enolate. And after acid treatment, I end up with this carboethoxy cyclopentanone. And so this is a very nice way to make a 500 grain. Now, let me remind you of a reaction that you know. And one of the reactions that we learned not so long ago was a decarboxylation reaction. Remember, we talked about the fact that if you have a beta-keto carboxylic acid, like so, that with mild base or acid and heat, you can split out CO2 and end up with a carbonyl. Okay, so remind yourselves of that mechanism. Now, in the context of the Claisen or the Dieckmann condensation, I think you can see what I'm getting at. That if I hydrolyze that ester, I end up with a beta-keto acid, which can undergo decarboxylation. And so this is going to give me, as a product, cyclopentanone. Okay? And so the Dieckmann condensation is useful because it doesn't just work for 500 grains and 600 grains. Turns out that reaction is quite general. It works for many, many different ring sizes. So it's a really useful method for making cyclic ketones. Okay, so that's the Dieckmann condensation. It's just a Claisen reaction. So the mechanism here is really no, I didn't go through it because it's the same as the Claisen, no difference. Now, just as we saw crossed alkyls, we have crossed Claisen reactions. And so you can imagine starting with two different esters where R1 is not the same as R2. Ethyl esters, so we're going to treat them with sodium ethoxide. We'll get all possible Claisen products. And if we get all possible Claisen products, I've spelled them out here, this is going to be a mess. And so this reaction is going to be useful only when I can suppress the formation of 3 out of 4. Okay? And so when might that be useful? Well, actually quite a lot. Look, diethyl carbonate is an ester. It's an ester of carbonic acid. Carbonic acid is H2CO3. Carbonic acid is not stable. It's an equilibrium between water and CO2. But diethyl carbonate is perfectly stable. You can buy that stuff. It's a liquid. It smells kind of nice. And it can't enolize. So there's no way, it's an ester that cannot enolize. Because it can't enolize, this can only act as the electrophile. And so if I use an excess of diethyl carbonate and this particularly enolizable ester, then this nucleophile can react with that electrophile to give this phenylmalonic ester. And notice the yield is really very, very good. So this is a crossed alkyl reaction to be sure, but of course it's a special case. It's a special case because only one of the two esters can act as the nucleophile. The other one is precluded from acting as a nucleophile because it cannot enolize. There's no carbon atom alpha to the carbonyl. So this is a very common crossed alkyl reaction. But it's not the only one. There's another ester that is very commonly used that cannot enolize, and that's ethylformate. Okay, so I take formic acid, H2CO2, right? Then I can use that as the electrophile, and I can start out with diethyl succinate, and because this is symmetrical, it doesn't matter which of the carbonyls enolizes. And I pick ethyl esters. And if I enolize it, I end up transferring this formyl group, this CHO, right, from there. So addition, tetrahedral intermediate, elimination. You guys need to write these mechanisms, and you end up getting this as your product. Now, the question you might have is, I have a diester. That diethyl succinate is an diester, right? Now, we just saw Dieckmann condensations of diesters. How come it is that I don't get a Dieckmann condensation? I mean, clearly, if I had started out with ethylformate, and not diethyl succinate, but with diethyl aditate, if I mixed this plus that, then I'd have a competition of the Dieckmann product plus the transfer of the formyl. But I don't see that. Why is that? Why is it that this thing doesn't do a Dieckmann? Come again? Well, it has to enolize, right? It has to enolize because if it didn't enolize, you wouldn't be able to form this product. This product formed from the enolate, or the enolate. So it can enolize because there's CH2 there, CH2, so sure, it can enolize. That's not it. Why doesn't it do the Dieckmann? Strain. Yeah, strain, because if it did the Dieckmann, it would form a 1, 2, 3-membered ring, and that's strain. So you don't need to worry about that one. Okay, now these are special esters, right? The ethyl carbonate, ethyl formate. These cannot form enolates, and they can only act as electrophiles. And so that's good. Can you think of another ester that can only act as an electrophile that really cannot enolize? I mean, those two we could say, wow, very much, these very special cases. Is there another one? Yeah, there's plenty of them actually. How about this one? The methyl group there, that can't enolize either. Or how about just phenyl? Can this enolize? No, because you don't have an alpha proton. No alpha proton, no alpha proton, no enol. So these can only act as electrophiles. And so the idea you should get is that, well, you know, these are special cases, but they're not limited to just ethyl formate and ethyl carbonate. There's plenty other cases that can be used. Now, this turns out to be useful because that formyl group is reactive and can be exploited in synthesis. And so the cross-alkyl, or rather cross-Claisen reaction takes place now not between two esters, but between a ketone and an ester is also useful. So we've seen, you know, alkyl reactions, aldehyde plus aldehyde or aldehyde plus ketone, Claisen reactions, ester plus ester, but there's nothing to stop us from doing this reaction of a ketone plus an ester. So this is a cross-Claisen, but it's not the same because it's not an ester and an ester, it's an ester and a ketone. This one can't enolize. Only acts as the electrophile. This enolizes, and so guess what? We end up transferring the formyl group out to the carbonyl. So this reaction and this one are essentially the same, it's just the enolate is different. Here you have an ester enolate, here you have a ketone enolate reacting with that carbonyl. So I urge you to look at the mechanisms individually for each and every one of these when you go home. I'll do it for you here. So you end up pulling off one of these protons with ethoxide. That's going to give you an equilibrium of the enolate of the ketone. Okay, now this is going to react with ethyl formate. Why? Because this carbonyl has a partial positive charge. And so I'm going to end up forming a tetrahedral intermediate from that process. With the formation of this bond, that one right there, there's the hydrogen, there's the ethoxy group, and there's the alkoxide that I got from here. That tetrahedral intermediate collapses the way they always do when there's a leaving group. And at this point, it's irreversible because I now have a very acidic proton here. That acidic proton gets removed, and I form an enolate in my as the initial product. So these mechanisms I want you to do by yourselves, not copying it off the book. Make sure you know what's going on. Then you'll understand this. This is not, you know, all of these mechanisms are the same, by the way. So once you do the first couple, the rest are going to be very, very easy. You need to do the first two. Okay, now once again, this cannot act as a nucleophile, only as an electrophile, and therefore you get only this product. But you can kind of there are ways to get around the problem of this cross-Claisen by using an excess of the ester. So here's a ketone. Here's ethyl acetate, and if you use an excess, you still get very good yields of the beta diketone. Notice this is a diketone, not a ketoester. Now this works really well for the following reason, that it's much easier to form the enolate of the ketone. It's much harder because there's a huge difference in pKa between this proton and that one. And so the only enolate we form is this one. And that suppresses any kind of the regular Claisen product. And so you can use the difference in pKa's to drive the reaction one way or another. Okay, so question and answer this afternoon at 4 to 5